Oh, I have to reshare this. Okay. So, okay, good morning and good afternoon and good evening. So welcome you again to this World River and Delta System Source to Think webinar series. Today, we invite Professor Sagy Cohen from University of Alabama come here talk about the global scale, sediment modeling in the large global rivers, the applications, challenge, and the future directions. So as always, before I introduce Sagy, and I want to tell you that coming Friday, we have other great talk. Brian Romans from Virginia Tech come here talk about sediment recycling in source to sink system, particularly focused on the Amazon River fan system and also the Magallanes Basin of Chile on the side of South America. So please mark your calendar as always and come back to this Friday, the same time. And also this week, the London and Paris still, a little bit one of the difference as always, still 1 p.m. and 2 p.m. Next week, of course, London will become 2 p.m. and 3 p.m. after the day saving time. So, okay, Sagy is get his bachelor and a master degree from Ben Gurion University, Israel, and PhD from University of Newcastle and the Environmental Science and Environmental Engineering Department. And so postdoc at University of Colorado with Joyce Whiskey, and also 2012 assistant professor University of Alabama until now associate professor. So also visiting scholar University of Hawaii. I think if I strongly recommended you visit his research lab website, the surface dynamic modeling. There's so many interesting stuff over there. So I think we're looking forward to his talk. Hey, Sagy, now you can share your screen and put a presentation mode.
All right, can you see it okay?
Yes.
All right. Well, thank you, Paul, for the invitation and for this incredible seminar series. I've enjoyed it very much. So when Paul invited me, and after attending the seminar series, or at least quite a few of the talks, I thought that one thing that may be of interest to this community is to talk about sediment modeling at large scale. And that's because quite a few talks actually use models or sediment models at different scales, and some of them looked at global perspective. And I'm actually going to link some of my what I'm going to talk today to some of these talks as well. Okay, let's see if I can. There we go. So some of my motivation, I don't need to expand on it for this audience. Obviously, we all know that freshwater systems are experiencing rapid transformation, a lot of stress due to population growth and economic development. On top of that, we have the stress of changing climate. So there is a real need for us to better understand the impact of all of these stressors and all of these changes for rivers or large river systems and their effect on coastal areas as well. So it's a very timely undertaking to try to really understand, but also really to be able to quantify how these different stressors and drivers and processes affect freshwater system at large scale. So why global models? So we all have seen and heard, and so many of you I'm sure have used sort of regional or basin scale models. What's the utility of global models? Obviously, they can give you a global scale of the problem or understanding, but also they offer a uniform platform that allow you to easily compare different locations, so have a more uniform understanding of the differences in space and time instead of trying to develop or calibrate a model to a specific basin based on an individual data set. So that's one of the attractive features of global models. And also they help, and I've found a lot of people use my modeling efforts to alleviate some of the chronic scarcity that we have in observational data globally, especially when it comes to sediment. Again, I don't think I need to convince this audience that that is a problem. I like to start my talks with this image that I generated in Google Earth some years ago. And I usually ask the audience, what river are we looking at? And I think for this audience, I'm sure many of you have already recognized it. It's a bit tricky because we're not looking from south to north. We're actually looking from east to west, kind of an oblique view. And this is, of course, the Amazon River. And the reason why I like to put this, first of all, I think it's beautiful, but also, as we heard a lot about the Amazon already with some great talks, we see a lot of the complexity that I'm going to talk about already here in one sort of image from space, basically. So we can see, for example, again, we heard a lot about the Amazon, so I don't need to expand, but we see, you know, the source of the sediment up here at the Andes mountain ranges. We see floodplain processes happening even from space. We see all this flooding going on here. We see interesting dynamics in sediment. So here's the Rio Negro here in Manaus and the confluence, the famous confluence of the two in Manaus. So we can see that already. And of course, we see the massive anthropogenic effect in form of deforestation happening all over the south of the basin. And as well, obviously very timely for or relevant to this seminar series, we can see the complexity at the delta at the coastal area. So my talk today, I'm going to focus on one model, the model that I kind of led the development on, and we're still developing this model called WBMsed. You may, so those of you who've been paying attention to quite a number of talks, this model has been used by a number of presenters in this seminar series. So I thought it would be of interest to describe it a little bit in more depth. And then I'm going to very quickly go over some of the application that we had and my colleagues have done with this model. And I apologize in advance for this section that I'm gonna kind of machine gun describe all the different application or selected application that we had. I'm not gonna go into depth. And some of them are really, really new. So I don't even have a paper for you to go to. But it's just stuff that I'm excited about and I want to share with you. So again, I apologize in advance. I know often people like to dive into a specific research project, but here I'm going to give a bit of an overview. And then I'm going to finish by looking at some recent advances in global sediment modeling that I identify and I think are really promising and interesting. And just a short discussion of thinking about some future direction and where I think the community can come together and help advance this whole field. So let's talk about the WBMsed model. This is a model that I started developing when I was a postdoc in Jaya Savitsky's group at CSDMS over 10 years ago now, and we're still developing it. It's part of a larger modeling project called FRAMES that was led by Charlie Vorismarty at CCNY. And it's an open source, global scale, spatially and temporally explicit, so it's a gridded fluvial flux model. It's built on a very extensive, as we said, biochemical modeling framework, and specifically the WBM plus hydrological framework. I'm gonna describe it a little bit more later. And currently the WBMsed include a number of modules that relate to sediment. We have a suspended sediment, bed load, that also include the suspended bed material and a particulate nutrient and organic carbon modules. And again, this is in addition to the biochemical framework that others, including Woolheim, have developed in the past. So this is the first paper we published about WBMsed. There's another one, 2014, that describes some of the version 2 of that model, and obviously a lot or a number of papers that use that paper. at that model. And if you're interested to get the code or look at the code, it is a fairly complicated framework. However, it is open source. You can definitely check it out and try to use it. There's been some groups all over the world that have applied that model. It's not easy, I'll just warn you, because it has a lot of input data that are needed. It's very specific in terms of the operating system that it uses and dependency. However, it is possible. So you can go to my website. We maintain a repository on GitHub using the CSDMS model repository, and as well as the WBM repository by Bolash. Okay, so we said the WBMsed is part of this larger hydrological framework. So I want to talk very quickly about it. It's called the WBM plus Global Hydrology Model. And I think this model is perhaps has not gained enough momentum that it deserves. Many people who do large-scale hydrological modeling, and especially global scale, tend to use something like VIC. VIC is a very good model. I have nothing against VIC. WBM is also an excellent model. And I think some of the advantages of WBM over some other global hydrology models is the fact that it's already a water balance and transport model. So it's all in one framework. So you don't need to deal with these different components. It also includes a lot of the anthropogenic effect, and very explicitly so. So we have things like groundwater uptake, for irrigation, for example. So here's the groundwater. We have the effect of crop of evapotranspiration. We have water uptake from reservoirs and rivers, and we have dams to control water flow. And obviously, each one of these components has its own issues, and none of them is, bulletproof for sure. But it's very convenient for us when, especially if we were interested in anthropogenic impact on river systems, to have all of these anthropogenic factors already built into our hydrological framework. And this is something, again, that's quite missing from a lot of these hydrological and sediment models that I'm going to talk about at the end of my talk. A bit of an addition that I made to the hydrological framework was introduced in version 2 of the model in our paper in 2014. That was an attempt to look at the floodplain and the retention of water and sediment in the floodplain. So it's a very simple approach that I adopted from Daya Mazaki's Camaflood model. This is a much simpler version of it, but basically, you kind of estimate the bankful discharge, and once you reach that condition on a given day, you store some of the water and sediment on the floodplain, and that help regulate sediment and water downstream of the flood. The suspended sediment module in WBMsed, that's obviously the main element that I contributed to. At this point, it's still based on the BQ-art equation, what we call Bogart equation, that was introduced by Savitsky and Milliman in 2007. Hasn't changed much since. We made some modifications to it. In a nutshell, what the Bogart equation is calculating is long-term average suspended sediment at the outlet of a basin as a function of its discharge, average discharge, drainage area, relief, air temperature, lithology. There's also an ice component. There's the trapping efficiency by dams, and what we call now AD, which is the anthropogenic sort of hill slope effect, sort of the effect of humans basically on soil erosion and anthropogenic effect. And I'm going to talk, this is a particularly problematic parameter because it's very, very simplistic. It's a categorical parameters that take population density and gross domestic GNP and try to estimate how rich countries, will conserve soil, relatively speaking, to poorer countries. We added sort of a land use component to it, but also this is still very, very simplistic. So the Bogart equation gives us, as I said, long-term average suspended sediment at the outlet of a basin. That's what Savitsky and Millerman did. What we do in WBMsed, we had a bit of a trick to it. In order to make it spatially and temporally explicit, what we do is we calculate QS bar, for every pixel as a function of its upstream area. So every pixel on the stream network is looking at its its upstream area, right? Its upstream basin, and calculate all of these parameters. And some of them are dynamic in time, like temperature and discharge and trapping efficiency and so on. So this is sort of a trick that we do, and I'm going to talk about the limitation of this approach. It works fairly well, as you'll see, but still it brings about a lot of limitation. In order to get to have the temporal component to it, so WBM provide daily discharge prediction, streamflow prediction at every pixel. And we use that with what's called the Psi equation. The Psi equation was developed by Moorhead and Savitsky in 2003. And it's basically a smart way to take the ratio, the daily ratio between daily discharge here and long-term average discharge at every pixel on every day. And the ratio between them multiplied by long-term average sediment to some power give you daily suspended sediment at that time and place. Now, the reason why I'm saying this is a smarter way to do it, because that C and Psi component can be a function or are a function of different parameter, including relief, temperature, and sediment. So it's not static in space and time, that C component, because each river, the non-linearity between sediment and discharge for each river can change in both space and time. That being said, so this is a smart way to do it, but it's also not bulletproof. There are problems with this approach as well. Very quickly about some of the other modules in WBMsed. We introduced a bedload model recently. I've not published it yet. This has kind of been very slow going in terms of publication for different reasons. But what we have at the moment, we introduced two bedload equations into the model and one suspended bed material equation. The first equation is following Kettner and Savitsky 2007 paper, and we used a modified version of the Bagnall 1966 equation. And some of the key dynamic parameters here are river slope, discharge, and water density. And I'm going to talk a little bit about each of these. So these are the main dynamic factors that we need to calculate in order to get bedload. I've also introduced, I should also mention my collaborator on this, Jas Savitsky, Tom Ashley, and Rod Lamars. We introduced the Lamars and Bledsoe 2018 equation, which is also a variation of the Bagnall 1980 equation. And it's quite similar in many ways, but it also introduced the representative grain size of the bed. So another dynamic factor. So this is the second equation that we have in the model. And finally, as I said, we have the suspended bed material. This equation was introduced by Savitsky et al. In 2019. And it also takes into account the settling velocity of the sediment, which is in itself a function of the particle size and water density and velocity and kinematic viscosity of the flow, again, as a function of water temperature and water density. So we have these three equations, and what we're working on right now is to try to analyze this and see that dynamics. I mentioned that we have a particulate nutrient and organic carbon component module in WBMsed. This was a low-hanging fruit that I worked with Albert Kattner, John Harrison, and Emilio Mayorga that we have yet to publish. So it's one of those low-hanging fruit that keep hanging on the tree. We haven't really, we did a lot of works over the years, but we have not published it yet. It's a fairly simple model, actually. So this is a series of 3 equations that were developed as part of the Global News particulate module by Mayorga et al. In 2010. So basically, the only factor here is the sediment concentration. So they developed those equations, and what I did is basically introduce them into the model, which allow us to calculate that in a spatially and temporally explicit manner. However, some of the difficulty for us is obviously to validate these things because validation data is quite challenging for these. So we have particulate organic carbon, particulate nitrogen, and particulate phosphorus, again following the Mayorga et al. Equation. So hopefully at some point we will publish that, but initial results were actually quite promising in terms of the model accuracy. So let me give you a sense of what this model looks like and how do we use it. So as I mentioned, we use within the WBM plus data frame, it runs at daily time steps. We simulate it at decadal time frame. It's a function of how much, or the range of your input data, and how much time you're willing to wait, and how much data you want to generate, right? So it can run for obviously longer time frames. But usually we use 50 years simulation. That's sort of typical for us these days. I run it between 1980 and 2019, or we can run it into the future as well. I'm going to talk about that in a few minutes. We run it at 6 arc-minute resolution. So that's a pixel size of about 11 by 11 kilometers at the equator. And it takes about half an hour to simulate 1 year. So it's not too terrible. It takes a little while, but not something too challenging. We run it on an HPCC. The reason being, you can run it on your regular Linux machine. It doesn't necessarily need a high performance computer cluster. It doesn't scale very well at this point. However, it generates a lot of data, and also it can take a while to simulate. So it's much more comfortable to run it on a supercomputer, or a cluster at least. What you see in front of you, this map, is a bit of a trick that we use in order to allow us to map this in a nice way that can actually be seen. Because once you try to map the output of this model at 6 arc-minute at a global scale, the pixels are too small to actually make much sense of it. Again, looking at the global scale. So we have a bit of a trick where we use the vectorize stream network, and we just extract the value to those features. And we also filter out all of the smaller rivers. We don't have a lot of confidence in them. So even though the model gives us gridded, so every pixel on the continent has a value, we filter out the small rivers. So in our case, we tend to filter out the rivers that are smaller than 10,000 kilometers square. Sometimes we go down to 1,000 square kilometers. It's really a choice of almost a cartographical choice, because if it gets too busy, you kind of lost the details from the forest in a way. So it's a choice that you can make of how much details you want to introduce. Now, a lot of people obviously are very interested in the accuracy of this model. That's very natural. As you can imagine, it's not very easy to validate a sediment model, because especially a global one, the data, well, now we have more and more data of sediment, which is great. However, the data is often problematic because it touches on different time frames. There's no uniform, right, data set out there, like you may even in the US with the USGS you do. Here's some results that I just did from just yesterday. I compiled these, and so we see at the bottom, this is 45 USGS gauge sites. I tend to trust USGS more just because, they have these continuous records and they're more or less uniform, more or less. That's kind of a key word. But we get really good prediction, and this is just average, right? This is not time variant. So we take, in this case, this is 40-year simulation. We average it and we compare to the average at each station. It should be noted that the time frame at each station do vary. So it's actually under predicting the accuracy in my view. But anyway, we get a really good R-square for water discharge, as you can see on these 45 stations, and a pretty good prediction for sediment flux. This is suspended sediment flux as well. So the model is doing quite well in most cases. Now, when you go to temporal quality on the temporal component, that gets you get a lot of variation. Now, you can run this model at much higher resolution regionally if you want to. On the left, we see a chunk of a simulation that I did for Australia at 15 arc seconds, so about half a kilometer grid size. The same for the US. And John mentioned that I was in Hawaii for sabbatical, and I did a simulation for Oahu at 30 meter. I had very high resolution climate data, so I did that, and the model did reasonably well without being calibrated. By the way, that's a question that I also get. We do not calibrate this model. So this is a global model. If you calibrate it, you may improve it some places, but you ruin it other places. So we have not been calibrating this model. Okay, let's very quickly talk about some of the limitation of WBMsed. So Bogart equation, it's an accurate equation, but it is a semi-empirical equation. So it's not, especially the way we represent it, is not necessarily mass conservative. It's not actually simulating the sediment transport per se, right? We're not moving sediment from one pixel to the next. We are not therefore representing explicitly any in-channel processes like bank erosion and so on. The anthropogenic impact on hill slope processes that I mentioned is extremely simplistic. And dam trapping, even though we have sort of the standard dam trapping module that was developed by Varis Marty and others, it's not very good, to be honest, at least not in the kind of modeling that we are trying to do, or the needs that we have to accurately represent dam trapping. So this is something that we're working on. For bed load, we have high uncertainty in the equation, right? It's bed load, so there's never a good bed load equation out there. It's very sensitive to river slope and particle size, which are two parameters that are difficult to represent at a global scale. We do, but again, a lot of uncertainty, and it's really, really difficult to validate, obviously. With the exception of a few case studies, you know, we don't really have good bedload data for large rivers. For the particulate nutrient and organic carbon, it's again a simplistic equation and does not have any anthropogenic impact to it and difficult to validate. All right, so let me talk about some of the application. Again, I apologize, this is kind of a machine gun presentation of these. I want to start with something that I really am passionate about, which is the anthropogenic impacts on sediment in large rivers. So we all know that we have sort of two conflicting processes or drivers of global or sediment in large rivers due to human activity. We're increasing sediment by soil erosion and other factors that increase sediment production, but also decreasing it dramatically behind dams. So there's been a few estimates over the year. What is the net impact of anthropogenic effect on sediment flux to the ocean? Varis Marty in 2003 estimated about 30% decrease globally. A more recent analysis based on gauge data by Lee has estimated a 20% decrease, a net decrease. Obviously, the story is very complex, and they found that Asia and Africa are the main driver of this decreasing trend. We did something similar, and this is some of the application of really the attractiveness of using a model like WBMsed, is that it allows us very easily to isolate the different anthropogenic drivers. So we have sort of different modes that we can simulate, pristine or disturb, that's what we call them, pristine mode or disturb mode. And actually we can do sort of semi-pristine. So we can switch on and off different anthropogenic variables in the model, both in the sediment module, but also in the hydrology module. So all of these anthropogenic factors like irrigation and so on, we can switch on and off very easily and simulate that. And then we just compare the two simulation, and that gives us a really good quantitative and spatially explicit understanding of these factors and their impact. So this is just a screenshot. This is a couple of maps from a master thesis by Sean Carter in 2016. So it's a bit old. We've done some improvement to the model since. So the story is very complex, right? As you can imagine, if you want to summarize this to at the continental scale, which is always sort of attractive because now we have simple numbers to look at. However, I don't know how useful it is because the story is very complex. But anyway, once you only look at the effect on hill slope, basically ignore dams or remove dams. So we see a huge increase in sediment to the ocean in different continents. Now, Asia here is kind of highlighted. I think we are way over predicting the increase in Asia. And I don't want to go into why we do that in the model, but I know that it's a major over prediction here. But the other continent, I think it's more reasonable. So about 10 to 25% increase in sediment due to anthropogenic activity if you don't include dams. If you do include dams, so now we see that Asia goes into zero because it's basically the dams balance the increase in soil erosion. However, again, because we are over predicting soil erosion here, I think this is under predicting the decrease in sediment in Asia. But anyway, let's for now not focus on that. So we see major decreases in Africa and Europe, in North America. Again, nothing too surprising. And if you average all of that, we see an estimated minus or decrease of 17% of sediment flux to the ocean, very similar to estimates that were done based on gauge data. Another application that's more relevant to, I guess, this seminar series is looking at river deltas. This was a paper that was actually presented a few months ago by Francis Dunn and Steve Derby. So I'm not going to go into that. They did a great job at presenting those papers. And so go, if you missed their presentation, it's on the YouTube channel. So go and check it out. It was really good. But in a nutshell, what Francis has done was to look at the future. So she used 4 RCPs, right, from a global general circulation model and 3 socioeconomic pathway. And she had an explicit layer for future dams. And so she looked at 47 river deltas and came up with the analysis of at the end of the 21st century, what should we expect in terms of sediment flux to these deltas? And not surprising, especially what was dominant in most deltas was dams and future dams. So the introduction of new dams that is quite apparent here on the left in many parts of the world. So again, I don't want to repeat what she presented already, but generally she finds an average decline of 38% in most of these deltas. Another excellent presentation was given by Jaap Nauthuis, and he presented a bunch of papers, including this one from Nature that he published in 2020. Again, he used the WBMsed model to look at the potential impact of humans on sediment flux, sort of retrospectively, not looking at into the future in this paper. And he has some, again, this is very complicated, right? And I'm not doing it service by skimming over it, but he did find that in many, about 1,000 deltas, river dams were resulting in severe reduction in sediment flux, but he also found that in about 25% of the delta growth that he observed with his remote sensing approach were due to deforestation, as he called it, or land use change or anthropogenic impact. Again, using the model to do this kind of thing. In my own group, we are also looking at deltas. So the Nuke Monashinga is a PhD student, was about to graduate, and he looked at details at about 45 deltas and did detailed remote sensing analysis of coastline retreat and delta plain land use changes and link all of that to sediment flux. And Nishani Morgoda, I'm going to talk more about her research. She is now working on really improving the model so we can better represent all of these complex processes in more details, and also look at extreme events. I'm going to talk about it at the end of my talk. I think this is something that's really important that we're not doing very well right now. So Nishani, for her master thesis, she published this paper. We published this paper in last year. And what she did was we wanted to isolate the climate change effect in the 21st century. So she used 5 GCMs and she created an ensemble of simulations with those 5 GCMs. And for each one of them, she had the 4 RCPs. So we have all these scenarios, right? Climate change scenarios. And she basically, what she did, she then compared the start of the 21st century to the end of the 21st century for each one of these RCPs. And again, this is complex, right? You see this map is just as an example for one of those RCPs, and the colors are red or warm colors are increasing in sediment, and blue is decreasing, and it's complex. There's a lot going on here. So I'm not going to go into that. I really would advise you, if you're interested, to look at the paper we published. If, again, you want to summarize these into some simple tables, again, this is attractive. I'm not sure how meaningful it is because the story is very complex, but it's always attractive to do that. So we do see that as you go to more extreme climate change scenarios here on, so from 2.6 to 8.5, we see an increase in discharge from 2% increase, again, globally, to 11% for RCP 8.5. And sediment is much more severely impacted, or more severely impacted by that, up to 16% for global sediment flux. And that's obviously, this is just the rate per decade change. So what we show is, even at the global scale, mitigating climate change will have quite a significant impact. Again, here we're only isolating climate change. We're not looking at other anthropogenic effects like dams. So a project that Nishani is leading right now is for her PhD work is to, as I said, basically the next generation of WBMsed. And one of the first things she's working on, and this is in collaboration with John Gardner and Tamlin Powalski, who developed this amazing algorithm in Google Earth Engine to observe suspended sediment at this point in the US, but can be expanded. It will be expanded globally. We're also working in the Amazon basin on that. And once I got working with John and Tamlin on this, just a few months ago, maybe a year ago, I got really excited about the potential of this because, as I said, one of the big issues that we have, and this is not unique to WBMsed, it's basically all models, is the fact that we really don't represent the effect of dams and land use change well enough in our models. And a big part of it is because we don't have the data. We just don't know really in reality what's going on. So this is a longitudinal profile of the Missouri River. On the left, we have the headwater. On the right, we have the confluence with the Mississippi. And we see the red points are large dams, or dams along the river, the main river channel. And so let's focus on these guys over here, Fort Peck and Garrison Dam, because they're a really large dam. And you can see, this is sediment concentration. You can see that drop, that massive drop in sediment concentration that happens hundreds of kilometers upstream of the dam. And this is because the reservoirs in this case are massive, are really long. And so this is not surprising, right? It's not surprising to see that. But now, right, we have a quantity that we can extract for each dam. And what's also very interesting, and you don't see it very, very clearly except for the Fort Peck Dam, but because of the scale, but we have this recovery, right, that happened immediately after each dam. I'm trying to highlight it here. So immediately after each dam, once you over downstream of the dam, we start seeing a recovery in the amount of sediment. Now, this is not surprising, right? We all know it's been well talked about that we have, when you starve the river of sediment, it starts bank erosion, is scouring and so on. But now we have the ability to quantify it for each dam. So if nothing else, and hopefully develop an algorithm or a model to actually explicitly simulate that in a more precise way. Because the way we do it right now, we just say, okay, the dam is trapping 80, 90% of the sediment, that sediment is gone, and we just remove it from the equation. Basically, we still do that. So we know it's much more complex. We know that now we can actually quantify this and model that, and I'm very, very excited about this. Another example that I just really like, so I like to present it, also really nice graphics. Another really cool application of this model, some work I did with Julian Leyland and Steve Derby. Again, not really published. We had a poster about it at AGUs in 2018, but not much since. I have a new student working on it, so hopefully soon. But what we did here, we basically expand on the work that these guys did and others, including Jim Best, at the Mekong, to look at the effect of tropical cyclones on sediment and water discharge in the Mekong. And the idea is, with this model, we can do it globally, right? So the approach is actually really, really simple. You simulate the model with your normal precipitation data set, and now you take the same data set and you manipulate it to remove the precipitation that is contributed, that is added by tropical cyclones. So Julian has an approach to do that based on the track of the tropical cyclones. So you can see on the right, on the top right, this image here, you can see the contribution of annual precipitation by tropical cyclones. So now we can simulate the model again and basically compare the two simulations. It's as simple as that. And what we found, this is, as we said, a bit old and not totally vetted yet, but we found about 2.3%. That's sort of the contribution of tropical cyclones to sediment flux globally, or about 17.5 billion. And that number needs to be worked at and looked at again. So it's not an insignificant amount just by tropical cyclone contribution. I think we are way underestimating this, to be honest, because as I said, part of our problem is that our ability to really simulate the effect of extreme hydrological events on sediment is a bit lacking. Another paper that was presented recently or led by Jaya Savitsky that I think opened up a whole suite of opportunities for us is looking at the effect of thermal dynamics or water temperature on sediment prediction and sediment in general. So one of the really nice attributes of WBM is its ability to simulate water temperature in a really robust way. This was recently improved by Ariel Miara, who was a co-author with Jim Best on that paper. And again, it's a very, I would really recommend that you check out this paper if you haven't seen it before. I'll just take you to the last, to the main bullet point, which is that the common practice of using fluid density and temperature constant, which is, fluid density of 1,000 kilograms for a cubic meter, in transport model can greatly underpredict subpolar and alpine river transport, that's in cold rivers, and overpredict sediment transport in tropical rivers. So one of the things that's really exciting about what came out of this paper, which was very theoretical in many ways, is that it opened up our ability to now really investigate these concepts that we, and especially Jaya, identify in this paper. So this is something that is already, as you saw, incorporated in the bed load and suspended bed material equations that we have. Okay, so that was the machine gun portion. I want to talk about some what I call recent development in global sediment model. It's been dormant. This whole field, I think, has been dormant for a long time, but has received quite a renaissance in recent years. The first model that I want to introduce to you is actually not very new. It's from 2012. So Peltier in 2012 presented a global suspended sediment model at the same time as WBMsed was published as well for the first time. And Peltier had a really cool way to approach this. He basically thought about sort of physically based, Peltier comes from sort of hill slope dynamic modeling, surface dynamic modeling, and he took his expertise into the global sphere, and he used physically based equation to try to estimate the detachment of particles from the hill slope and the channel, and then either a transport or deposition within the channel itself based on the Rose number. And it's a really neat approach. The kind of the limitation that model had, that it's not really built in or yet to built in into an hydrological framework. So it's a bit hard to, I think, use it as an analytical tool yet. Although I may be just I'm not sure if there's been more recent development in that. And it also has some temporal and anthropogenic limitations. So it doesn't really represent, to my knowledge, the hydrological, the temporal and anthropogenic dynamics in those systems. But I think it's a really interesting model that's worth looking at. More recent development, and again, there's been quite a few in the last couple of years. A lot of it has to do, but not all of it has to do with Earth system modeling. So Zili 10, he developed a sediment component to the E3SM. E3SM is the Earth system model for the Department of Energy. So a lot of the national labs in the US use this model. It's a community model. And over the years, they recognized the importance of sediment in the carbon cycling of the planet. So they got really interested in the fluvial component of the Earth system. And so Zili at 2018 published this review paper or analysis that he looked at different models, basically tried to identify the best soil erosion model that he should use in his model. He actually identified the Morgan model as being the one to use. So here it is over here. It's a fairly simple model. It does use rainfall intensity, which is a bit difficult to simulate explicitly, but the Earth system models can do that apparently quite well. So by the way, so Zili 10 has a bunch of other papers, subsequent papers about this model. So again, very worth, it's worth looking at those papers, because I think using Earth system models is the future for us as well. And I'll talk about it in a few slides. Another paper that came out in 2020, just recently, Hatuno and Yoshimura developed this really interesting model that explicitly simulate the suspension and deposition of sediment within the channel, within the flow itself, and also represent the connectivity between the floodplain and the river. So they use the Kamaflood, the Yamazaki Kamaflood model to represent the floodplain and to make that connectivity, albeit it's quite simplistic compared to their channel dynamics. They have really good results in their paper. So they have pretty accurate results there. So I think this is a really promising new direction, this very explicit representation of processes, especially within the channel. Some of the limitation, it's not yet fully integrated into a hydrological framework again, so making it's a little bit less, I guess, ready for this kind of analytical application. It doesn't have dams, to my understanding, and also it's not open source, although they said that if you contact them, they'll be happy to share. There's been a number of publications recently that use the USLE type equations and translate that into sediment flux. So those of you who are not very familiar with the soil erosion modeling discipline, so USLE was developed in the 1950s to represent soil erosion from agricultural field. And it's been developed ever since. It's always been developed. So there's many variations, including Russell, the revised USLE, and Muscle, I think the modified, I think that's what the M stands for. And a number of publications have came out recently that apply these variation at the global scale. And the attractiveness of that, even though it's a very simple model, empirical model, the attractiveness of using these USLE type models is that it's all about human interference to the landscape. Well, not all, but a lot about, has very explicit parameters like agricultural practices and conservation and so on. So in terms of understanding the anthropogenic impact on hill slopes, I think this is very attractive, and it's simple enough that you can simulate or you can calculate that at high resolution at global scale. So Baroli et al. In 2017 have a map out there at 250 meter soil erosion. Actually, Nishani, my PhD student, she just did something similar in Google Earth Engine. So we can now, especially with Earth Engine, we have all this data that we need. Grill et al. With this seminal paper in Nature about mapping the world's free-flowing rivers, they took the Baroli dataset and had a smart way to route it into sediment to estimate the sediment trapping index in their analysis. So I think this is very promising as well. So Zhang et al. Just this last year, they developed another one of these style models to estimate sediment and organic carbon within a land surface model. Again, there's this land surface modeling community that's really interested in sediment as a conduit for organic carbon. So anyway, in a nutshell, what I'm trying to show you, there's this approach that's been prevalent in recent years of trying to think more physically based. There's also this approach of, okay, let's look at anthropogenic effect with even relatively simple equation, but we can do it easily and at high resolution. And I think all of it is very interesting and very lively right now. So I'm very excited about the future of global modeling of rivers. So let me conclude with some final words about future direction. So I think I hope I proved that global river models are quite useful, or can be quite useful, and they are needed. They allow us, especially with some work, to understand the effect of climate, of humans, of geomorphology on sediment flux in river system, and as a result, obviously, of what's going on or what's coming out into the coast and the oceans. However, there's a lot of work to be done. So my vision, what I think needs to be done, we need to look at those really recent development that I just outlined and look at how we build on them, right? We don't want to mimic, we want to build on the recent advances and make them better and better together, hopefully. So I think there's a lot of potential of creating a much better global sediment, both suspended and bed sediment transport right now. One thing that's really challenging, especially from us as geomorphologists or hydrologists, is to understand the very complex interconnectivity we have between climate and anthropogenic drivers, right? Because climate, we can simulate climate by itself, as I showed you. We can simulate and analyze anthropogenic effect by themselves, but the two are not mutually exclusive, right? They affect each other dynamically. So changes in climate affect land cover, affect agricultural practices, affect human settlement, right? So this is very complex. We don't know how this is really going to look. How is the landscape really going to look? Because there's a lot of things we just don't know. So it needs those people who can estimate those things or know how to think about those things to work with us on that. One thing that I think is quite crucial is to think of extreme hydrological events. Now we all know, right? Once there's a flood, the water turned brown, there's a ton of sediment or many tons of sediment transported in a very short period of time. We know that, we've all seen that, not surprising. How much? We don't really know, right? Even if we have a gauge site, that gauge may not really give us the true result out of it. So, and definitely models are not very capable or not very sensitive to these extreme events. Maybe the physically based model will do better, but we need to figure that one out. We need to figure out what is the contribution of extreme hydrological events. And extreme doesn't have to be 1 in 100 years. It can be 1 in 2 years. Even that we don't necessarily know, especially globally. So this is something that I'm actively working on. I think that's very, very important, especially for deltas, right? Because again, we know that deltas rely on these floods, right, to flood the delta plain to deposit sediment, right? So it's not about averages. Averages are important, but it's not just about averages. It's about those extreme events as well. So we need to work on that. So, and also the last point here is we need to think about the sort of so what kind of question. Okay, so we can do sediment and hopefully can do it better in the near future, but how does it affect ecology? How does it affect deltas, geomorphology, water security, and so on? We need to talk to the people who know how these things work at that end as well. So finally, my vision and sort of my long-term goal is kind of borrowing from the climate community, right? They develop over many years and with huge collaboration and funding these GCMs, right? Many GCMs to predict the future of climate. So I think we need a fluvial GCM, right? A fluvial, a way to predict what is the future of rivers and do it in a very, with a lot of, with confidence, right? Really increase the confidence in our prediction. Climate, humans, everything in between, right? We need to do a better job because it's very important and very timely. So I think this is all the time I have. So I'll thank you for your attention. Feel free to shoot me an email, visit my website, and generally just have a chat. Thank you.
Hey, Sagy, thank you so much for this fantastic talk. And I really, really like this kind of a big picture, global scale, because there's many of our colleagues, sometimes students, you know, they look at the tree leaves or branches, they miss the whole forest. So that's a great work we need. Okay, if you have to leave soon, I know many people rushing to leave in 2 minutes. If you have a quick question, go ahead to ask a sec. Let me unmute. Now you can unmute yourself. Anybody? I know Jim Bester is leaving. Yeah, Jim, go ahead.
I can stay today. Yeah, thanks, Paul. Hey, Sagy, thanks. That was great talk. Just fascinating putting it all together. I was just going to ask you one thing about, right at the start, you were talking about the floodplain connection and routing sediment or water into the floodplain, that floodplain connectivity. And that's done through, is it, you say, just a bankful discharge? So yeah. Two questions. One, in terms of, say, looking at a lot of rivers where you have embankments or levees or whatever, how influential is that? And also, presumably also the connectivity between river and floodplain is also through, you know, channels that also feed sediment and water out onto the floodplain. So is there any ways, especially for bigger rivers like the Amazon or the Brahmaputra, of building in that sort of porosity between the channel and the floodplain, you know, to make that connection more realistic, or does it not matter?
I don't know the answer for if it matters or not, but the component that I introduced is super simple, right? It just say overbank, it goes there. It doesn't really do anything. However, that paper that I showed by that group from Japan, they now have that camouflage model that have a much better representation of the floodplain, its topography and so on. And they look at it more from a hydrological perspective because the camouflage is a flooding model. So it looks at water flooding. So I think that has a lot of potential of addressing those dynamics on those details. But, you know, when it comes to embankments and levees and so on, often the problem is the resolution of the data. You may not know that they're there, and they can be extremely important in terms of whether or not you actually get any water on the floodplain. So absolutely, yeah, that's I'm also very involved with the sort of the hydrological community for flooding. So they are very interested in that, but it's a function of resolution a lot of time.
Okay, thanks, Sagy.
So go ahead, Tom, you have a question or?
Yeah, I can ask a question. It's actually very good talk. I also sent you a comment that you can think about with some things we're getting involved in. It's sort of related to that comment. We're interested in looking at sort of this pulsing of export along the eastern seaboard in U.S. In terms of how these storms sort of moving in and out through North Carolina in particular are exporting carbon, to the coast, and what that means in terms of CO2 uptake and release. Does this model? I mean, I saw that one Leland reference you talked about. I'm not sure if that resulted in a paper or you were saying that was an abstract, but it sounded like you sort of got close to this kind of question, whether it's particulate or dissolved, but we're interested in sort of the replenishment of the terrestrial system after you export that, and this sort of seesaw balance between what's lost and what shows up in the coastline in this pulsing. Does this model have some version of what you talked about today have some applications for that?
Well, potentially, right? But I try to be very brutally honest about the simplification that we have, right? So the only, at the moment, with the current organic carbon equation, it's just a function, empirical function of sediment concentration. So we know it's simplistic, right? We know that, and at the global scale, it works okay. So, and in terms of storms, again, the problem is I think it's very safe for me to say that we are underestimating the effect of storms on the amount of sediment that comes out. And that's a really point that we need to work with. Given those limitations, right, we can simulate stuff, or we can run the simulation. And if we have data that can be compared against, it may or may not look okay. I don't know. Also, always when you do this kind of global modeling, you find that sometimes in some rivers that you're interested in, it's doing horribly. We know that, right? So a lot of people come to me and take my output results and they get disappointed. Well, hopefully not a lot, but some people, because they say, well, it's way too much. We know that it doesn't produce that much or that little or something. And I acknowledge that, absolutely. We can be, and over the years, and some of the papers that Francis has also did recently, some validation, it can be over an order of magnitude sometimes off in some rivers. Overall, most rivers are within, but yeah, we can be off. Anyway, short answer, yeah, we can simulate it, but given the simplification, we need to be careful about how we analyze it. So if we have some data, that's good.
Okay, thank you very much. Stay tuned. We may be in touch with you if you're interested.
Sounds good. Yeah, always.
Okay.
So I think Tom mentioned the North Carolina, particularly the hurricane landfall caused the carbon export. I think Hans Paul's talk is definitely one of the things we must to watch. The great summary of 25 years observation. But anyway, Sag, anybody else? So when you prepare a question, Sag, I have a question. I like the way you try to understand the hurricane, the tropical storm impact to the global sediment and the global river and the water discharge. So that's great. We need to understand that. But in terms of the natural change, like global warming caused the meltdown glacial, and your model show which river basin system have a dramatic change. I know human impact we can see, like Yellow River, Colorado, Mississippi, Nile. We know that pretty well when human caused a dramatic change. But the natural change sometimes is subtle, sometimes is not that dramatic. But your model able to show that kind of global warming impact, like the Russia River are always interested in, like, you know.
So we have in terms of climate, temperature and precipitation are explicitly incorporated. So these, when it comes to glaciers and ice, generally, the model is backward in a way, because we have a glacier parameter in the Bogart equation, and it increased the amount of sedimentation when you have glacier present in the basin, and that makes sense. However, climate change actually reduced the size of the glaciers, right? We know that produce a lot of sediment, but the model is backward because that will reduce, in a way, the amount of ice and therefore the erosivity out of ice. So we need an explicit way to say, once glaciers are melting, right, they start pumping a lot of sediment or introducing a lot of sediment. So it's in a way, so long term, so when you compare different basins, you say, okay, this basin has some glaciers upstream, so it has some contribution to sediment, and that basin doesn't have it, so it doesn't. But it doesn't account for the temporal changes in ice.
Exactly.
So so the answer is no for ice. Basically, we're not doing any.
I mean, that should be a very interesting thing. You know, at the beginning increase, then if there's no ice left to melt, then sharply decrease. I mean,
yeah, I mean, to be honest, this is not something that I've been very concerned about, just because that at the global scale, at the basin that we look at, I don't think that at the scheme of things that is the big factor. However, you're right, in some basin it's huge, right? It's everything. Go to Greenland. We heard some great talks about Greenland for sure.
That's cool. That's good. That's good. Anybody else? Okay. Yeah, I think the carbon component for the future, there will be really something. We not only need to understand water sediment, but the carbon export, you know, use the modeling, global river scale. Okay. If no any other question, I think, Zach, thank you very much. Once again, this talk is also available on the YouTube, and so you're welcome to rewatch them. And I see there's also, let me see, Zach, are you able to check the chat?
Yeah.
You could put something, let me see, a comment or question.
Yeah, we have a comment from Hugo. I don't know if he's still here.
He said also the
yeah, I'm here.
Here you go. So what was your question again?
I'd like to know your opinion about the use of Usley family models to equations to estimate erosion and sediment yield, because a lot of sediment models use this approach, use these models, but sometimes we still heard some complaints about this, some critics about the use of these equations.
Yeah, you know, absolutely. You're absolutely right. I mean, this is it's in some ways it's surprising that there's such a resurgence of the USLE family, because it is a very old model, or at least the initial model. But I think, again, my sense of it is because it's simple, it's attractive at the global scale. And also because of its explicit representation of anthropogenic effect. So Baroli, I think, I would refer you to their paper in 2018, and they did a pretty extensive validation analysis at the global scale, and they seem to show really good results. So I trust that they did it well. So I think it's promising. We haven't used it yet to do any kind of sediment modeling. Also, the connectivity between, so USLE style model represents soil erosion. the fact that you have soil erosion doesn't mean that all of it is going to end up in the channel. So, and once it reaches the channel, what's going to happen to it as well. But so the connectivity between the hill slope and the channel is also something that you need to think about if you want to use USLE style equation or any soil erosion equation for sediment flux modeling. So there's potential there, but you're right to be skeptical, or there's some skepticism about the applicability of it. But a lot of smart people seem to be doing a lot of good things with it. So I'm hopeful that it's useful.
Okay, thank you.
All right, Paul, thank you so much for the invitation.
Okay, it's a great, Sagy, it's a great talk, and thank you. And so I see you, everybody. I see you Friday.